Hi, I'm Limulga, and I'm from PCED 06501A. So today I will be discussing the analysis model, non-isolated system, momentum. Next. Okay, next. So here is the introduction of my topic. So in classical mechanics, the study of motion involves understanding the changes in momentum experienced by particles and systems. According to equation 9.3, the momentum of a particle changes when a net force acts upon it. Extending this concept to a system, section 9.7 explores how the momentum of a system changes in response to external forces. This parallels the discussion of energy transfer across system boundaries in Chapter 8. In this section, we delve into the analysis of non-isolated systems, considering them non-isolated, non-isolated, non-isolated when a net force acts on the system for a given time interval. So here in introduction, the introduction sets the stage by reminding the readers of the fundamental principles of momentum and I mean Newton's second law. It emphasized the idea that the momentum of a particle or system changes when a net force acts upon it. By drawing parallels to the discussion of energy transfer, the introduction hints at the exploration of non-isolated system and their connection to momentum changes. Next is the impulse and momentum change. So to comprehend momentum changes in an isolated system, Newton's second law is revisited, expressing the rate of momentum changes for a particle under a varying force. The momentum change equation is obtained by integrating this expression. The concept of impulse, the integral of force with respect to time, is introduced as a critical idea, represented as the area under the force time curve. Impulse is a vector quantity. The impulse momentum theorem formalizes the connection between momentum change and impulse, serving as a cornerstone for conservation and being equivalent to Newton's second law. This theorem, encapsulated in equation 9.10, provides a foundational understanding of the dynamic system momentum altera- alterations. So, this section deepens the understanding of momentum changes by revisiting Newton's second law and introducing the momentum change equation. The concept of impulse is explained as the integral of force over time, leading to the impulse momentum theorem. The theorem stated that the change in momentum is equal to the impulse imparted by external forces, providing a mathematical link between force and momentum changes. So next, characteristics of non-isolated systems momentum model. Comparing the impulse momentum theorem with the conservation of energy equation reveals notable distinctions. Equation 9.10 is a vector equation emphasizing the importance of directions in momentum considerations. Unlike energy, which can exist in kinetic, potential, and internal forms, momentum has a singular type, simplifying its storage and transfer mechanic, mechanicisms. This unique nature underlines the specificities of the impulse momentum model. So here, my report explores the unique characteristic of the impulse momentum model. It contrasts this model with the conservation of energy equation, highlighting that the equation 9.10 is a vector equation, bringing directionality into play. The singular type of momentum and its straightforward storage and transfer mechanism, mechanisms are discussed, paving the way for practical application. So next, time average net force. To facilitate practical calculations, a time average net force is introduced, defined as the mean value of the force over a given time interval, or equation 9.12. This concept allows for simplified expression of impulse, equation 9.13. The time average force proves useful, especially when dealing with varying forces over time. So, the concept of a time average net force is introduced to simplify practical calculations of impulse by calculating the mean value of force over time interval. My report shows how this can be applied to equation 9.9. This section emphasizes the utility of the time average net force, particularly when dealing with forces that vary over time intervals. Next, impulse approximation. In scenarios where forces vary with time, the impulse approximations becomes valuable. This approximations assumes a short duration force acting on a particular, I mean, on a particle significantly greater than other forces present. This is particularly relevant in collision scenarios, such as baseball struck with a bat. The impulse approximation, represented by equation 9.13, allows for the simplification of force considerations during brief interactions. So, this section addresses scenarios where forces vary with time, introducing the impulse approximation. My report explains that this approximation is particularly useful in situations involving short duration, high magnitude forces such as collision. The approximation simplifies calculations, offering practical tool when precise force details are not available. So, lastly, conclusion. In conclusion, the non-isolated system or momentum model provides a comprehensive understanding of momentum changes in response to external forces. The impulse momentum theorem, akin to Newton's second law, serves as a powerful tool in analyzing and solving problems involving momentum alterations as we explore non-isolated systems and their characteristics. The vector nature of equations and distinctions from energy consideration become apparent. The time average net force and impulse approximation further enhance the practical application of these principles. This analysis model contributes significantly to our understanding of classical mechanics, particularly in scenarios where momentum plays a crucial role. So, this conclusion provides a summary of the key concepts explored in my report. It reinforces the importance of the impulse momentum theorem as a powerful tool in classical mechanics comparable to Newton's second law. The section highlights the practical application of the time average, net force, and impulse approximation, emphasizing the role in solving real-world problem related to momentum. In essence, the report navigates through fundamental principles, mathematical relationships, and practical tools associated with non-isolated systems and momentum changes. It provides a comprehensive understanding of how external forces influence the momentum of particle and systems, offering valuable insights for problem solving in classical mechanics. So that's all. Thank you. See you next time. Bye.